Most digital mixing consoles operate on strict one-dimensional routing paths. An operator sends a signal to an output bus, and its position remains static. To create a dynamic spatial environment, engineers typically route these signals out of the console entirely. They rely on heavy external DSP hardware engines, equipped with independent delay taps to calculate physical acoustic movement. Spatia operates on a different premise. It bypasses the need for external DSP entirely by introducing a localized software layer that actively hijacks the console's existing aux matrix. Instead of an operator manually programming individual send levels, software mathematically translates a two-dimensional stage geometry into real-time bus percentages. The system scales up to 24 separate spatial speaker zones, mapping them identically to the 24 physical aux buses available on the hardware. Executing this architecture requires shifting focus from custom audio hardware to the management of high-speed software telemetry and deterministic state. The first requirement is a unified geometric plane. Physical speaker arrays and virtual audio channels must share the exact same X and Y coordinate system. This interface illustrates the spatial grid. Concentric rings act as distance markers. Perimeter squares denote physical hardware, arrays, fills, and subwoofers. When an object moves, dashed lines indicate the exact signal strength routing to each zone in real time. This abstraction extends to group control. An operator can define 8 separate vocal channels as a single spatial centroid, moving an entire choir section as a unified block. A single drag action by the operator instantly triggers dozens of relative geometric recalculations across the entire matrix layout. These geometric abstractions require a secondary layer of mathematical models to dictate how acoustic energy dissipates across the calculated distances. Applying simple linear panning across a multi-zone immersive rig fails in practice. The acoustic transitions near boundary edges become too abrupt, destroying the illusion of physical space. Spatia relies on 2 spatial rendering formulas for signal amplitude. The equal power calculation ensures perceived musical loudness stays constant as a sound moves. Conversely, the distance law formula drops the signal off rapidly, preventing acoustic bleed into far-side speaker arrays. A configurable zone spread parameter dictates the effective reach of these curves, dynamically scaling how widely a sound blends across adjacent nodes. Calculating these non-linear formulas for dozens of dynamic objects per frame generates a massive, continuous computational payload, and that data must safely reach the mixer. The data volume scales aggressively. A 10-channel choir across 24 zones generates 240 updates every single frame. If the WebSocket connection fails, an offline mode fallback immediately isolates the user interface, preserving all geometric data safely in memory. Rapid WeConnect logic stands by to reestablish the socket and resync the matrix without dropping the live geometric state. Moving data at this velocity bypasses the hardware limitations, but it introduces a severe computational vulnerability when managing conflicting commands during live show automation. Live audio automation operates on a strict rule. The show state must remain entirely deterministic and perfectly reproducible, regardless of external interference. This panel demonstrates how Spatia enforces that determinism. It plots the X and Y spatial coordinates against an internal timecode mapped directly to specific bars and beats. The software utilizes Catmull-ROM splines to draw smooth mathematical interpolation curves between the recorded waypoints. To guarantee absolute frame accuracy, this internal timeline synchronizes directly with incoming MIDI clock or LTC SMTP timecode signals. Operators can trigger a solo edit to manually intercept a grouped object mid-automation, adjusting its path without corrupting the broader recorded scene state. The platform also accepts external show control triggers via QLab, receiving coordinate instructions through Open Sound Control, formatted as UDP packets. This creates an immediate race condition risk. An automated OSC recall command could arrive at the exact millisecond an operator physically drags an object on screen. Spatia resolves this conflict through a strict hierarchy. Queue-based determinism immediately overrides manual input, protecting the show's integrity. The user interface, the spline math, and the network transport integrate into a single cohesive live state engine. The architecture successfully takes unpredictable, chaotic operator inputs and orders them into a perfectly synchronized stream of show control telemetry. The pipeline executes in milliseconds. An object is dragged, the panning formula calculates the falloff, the throttled WebSocket delivers the payload, and the physical console fader moves. This full stage view highlights the resulting system. The software layer effectively treats the physical console as a passive spatial matrix. Because these processing layers remain strictly isolated, the system can instantly recover from malformed OSC strings or partial hardware disconnects. Standardizing this two-dimensional matrix provides the exact data foundation required for future expansion into z-axis three-dimensional height rendering. The architecture is primed for advanced DSP integration, laying the groundwork for per-object multi-delay routing and direct binaural downmixes for in-ear monitors. Spatia demonstrates that highly sophisticated immersive audio rendering can execute entirely within a software control tier, upgrading static hardware limits without requiring a single physical modification.